All right, good afternoon. Let's get started. I'll say good Friday. Right? Okay, so today we're going to divide into two parts of this class. First part will cover chapter 7 about some theory or theoretical analysis about stresses, and then we'll leave some time, maybe like a 20 minutes so time, and give the exam 2 back, and then see if you have any questions about that. Okay. All right. So far we have been talking about all different structures. I mean the elements, right? So we talk about if you have a bar, if you apply axial load, we know how to do analysis, get the stress, get the strain, deformation, and then we talk about shaft when you twist something, right? How you do the analysis, and then we talk about beam. Right, load, stress, deformation, all that. Okay, so that's the 3 basic structures we learned so far. And then the next chapter, the very last chapter, we're going to talk about same thing like a bar, but under compressive load, we call column. So that's another type of model, structural model we're going to study later on. That's actually after exam 3. So in between this, today we're going to talk about more about the stress. So before we always look at the structure, right? How a bar structure deform. Now what we're going to look at is, don't look at the detail. What's the structure? Just look at a point within a structure. It can be any structure. Look at the point, right? One spot in this building or one spot in your body. Okay. What kind of stress is there, or what kind of strain is there? So what we call this stress strain analysis. So we might look at just one point. Remember, we just look at that one point, okay? But instead of looking at one coordinate, we're actually going to rotate the coordinate. So we'll see, if you stand upward, you see the stress. What if you lie down? What the stress will be? If you say 45 degree or any degree, what the stress should be? When you cut the element, all different ways, how the stress going to change, how they're going to, vary. That's what we're going to look at. So the stress analysis. Then we can figure out, answer one question. That is, if I have something there, right? There is a spot, very high stress. Okay, it's going to fail this spot. But let's say generate a crack. Which way the crack is going to be? Right. So the crack can be 45 degree, as we talked before, or maybe somewhere 30 degree or 90 degree. So you can basically figure out which direction is the maximum stress direction, and which direction will be most likely the failure direction. So remember, we'll just look at the one spot. 1 point, so stress analysis. All right. So in general, when you have an object, right, any object in the body or a building, if you look at the 1 point, right, the load can come all 3 directions. So therefore, the stress can be all 3 directions. Right? Is that correct? So we'll make it. That's just repeating what I just said. Right. So we'll look at the one special situation. We want to always start with something easy, simpler, right? So we're going to look at one special situation. That is, we call plane stress. Okay, so what's a plane stress? By word means everything on one plane. So it's 2D, not 3D. That make it much easier, right? You don't have all the 3-dimensional. We all know based on calculus, based on other analysis, statics. So the 2D are always easier, simpler mathematically. Right. But in principle, they are the same. The theory, the concept is pretty much the same. So we'll just use the 2D as a simple example to show some of the relations that we can do about the stress. Right. So therefore, we look at 2D plane stress. Okay, now what's a plane stress? By definition, everything within one plane. So the stress are within one plane. So as you can look at the picture here, you can see there, the stresses. If you look at the 1 point, there may be tension, there may be shear stress. The stress can be 2 components on any surface, right? You can have a shear component and a normal component. Right? But if you don't have anything in this 3rd dimension, so you have everything in the XY plane, XOY plane, nothing in the Z direction, then we call it plane stress. Right? So no stress in the Z direction. So we don't have any normal stress in this direction, or we don't have any shear stress that's going in this direction, right? It's like you have this block here, right? For example, this block here, right? It will be plane stress if all the stress here, here, and all this direction. But on this plane, there's no stress there. No shear this way, no normal stress this way. So that's the plane stress condition. So we define this because this is a simple situation. The analysis, everything will be easier. The equation will be. Okay. So here are a few examples of the plane stress. Okay. What's the first one? Where does this first one come from? This kind of stress. If you look at the spot, it's okay. Only two normal stress in this direction. Okay. Which element we learned so far that can have a condition that the stress will look like this? Tensor, right? When you have a bar, if you stretch it, you look at any spot there, the only normal stress. We talk about you cut cross sections, right? So there will be only normal stress. So that's basically a tensor condition. Any other possible element? We learn a shaft, bar, and also beam. Can this happen in any part of the beam? This kind of stress. At one point, there's only tension. Can this happen into a beam, inside a beam? Yeah, because if you have a beam, let's say you have a pure bending, right? Remember we talked about pure bending. There's only normal stress along this actual direction, and that is this condition. So it's very representative. It can be any structure. Okay. So that's the condition. We call actually this one, because it's so common, we have a name for it, called uniaxial stress. The stress only in one direction. Okay, that's one. Okay, now look at the picture on the right. We saw this before in shaft. If you look at the surface, a block of the shaft, or a spot of the shaft, right? There are only shear stress. Torsion generated shear stress. And that is like this. Okay. So is there anything perpendicular to the surface of a shaft? Yeah, a shaft, if you have a shaft, something you twist there on the surface, perpendicular to the surface, any stress there? No. So it's 0, right? So that's the z direction, the third dimension. There's no stress. So therefore, that's a perfect 2D plane stress situation. Okay. I think there are more examples here. In a beam, we talk about a beam, right? So if you look at any point in a beam, for example, pick one cross section, right? You can look at the point A, B, C, D, E, right? The stress on this part. Okay, if you look at the point A, that's the picture here. So this point, very top, there's no shear. It doesn't matter if you have a shear force there, but on the very top bottom surface, shear stress is always 0 in a beam. So that's a condition. So that's like a uniaxial condition. That's plane stress. There's nothing in this direction, right? Okay, so then the middle, you're going to have shear and normal stress. But still, nothing in the z direction. So it's plane stress condition. Right? In the very middle, shear maximum, normal stress, bending stress are 0. And that's what will look like this one. And nothing in the z direction, so it's plane stress. So basically, when we talk about the beam, we talked about before, right? We consider only the 2D structure. We don't consider beam have load this way and up-down way, right? So therefore, always we talk about 2D beam, and that is perfect 2D plane stress example. So we already see lots of examples. We just didn't mention that's a plane stress. So now just clarify, oh, this is the condition we call plane stress because there's nothing in the z direction, stress-wise. All right. Okay, so in general, there are actually a few slides. Let me jumping down to some more examples. Oh, where are my example? I think it's maybe using the wrong file. Let me pull up a different file. Not recognize this USB. Sorry, give me 1 second. Let me get the computer recommend. Okay, here it come up. Okay, here's a slide I want to show. So there are a couple of real-life example that this kind of structure always we treat as a plane stress. Okay, so for example, if you have a wall there, if someone is pushing from the side, okay, from this left side, I'm not meaning from the front side, okay, I mean from the left side. If someone pushing here, this is a structure, very thin in the z direction. So in the z direction, basically you can treat through this wall thickness. Everywhere in the z direction, there's no stress. Someone is pushing from the left or right side. In that situation, we call plane stress. So the most common situation we have a plane stress is you have a plate, a thin structure. The third dimension is really small, like a sheet. Right? So if you have something here, like this sheet, you stretch on, or you pull here, or two of you push both sides. Pulling on both sides, and that's a plane stress perfect situation. So nothing in this direction, across the thickness. Right? So that's one. Okay. Of course, if you have the same structure, let's say someone pushing this way, so this bending, deforming this way, then that's not called plane stress. Right? Because this plane, there is in the z direction, there is stress there. Okay. So here are a few examples, more examples. Like that gear there, everything, all stress, the interaction is within this plane. So you can sometimes, if you want, you can treat that as a plane stress, nothing in the z direction, right? Or if you have like this one, right? So if this is the base there or the floor, and you compress on, this is a plate, you press on the top, or you when someone maybe stretch on this side as well, and then that's a plane stress. Okay, so if you have a plane, all the load that within that plane, then that's a plane stress. Perfect example. Okay, so here is one. This structure we call a gusset plate. So that everything pulling or compression, they're all within that plane. So sometimes you can treat. If this is a big one, big plane, you can treat that. Okay. So the character, common structure that you treat as a plane stress is this dimension, XY dimension are big. But the thickness dimension are relatively very, very small. So you can pretty much treat as, basically it's the plate or a plane, then you treat as a plane stress. Right. So that's an example you can, actually here, this one, even there is a hole in the plate. Because everything, all the stress there is within this X or Y direction, within this plane. So we call it plane stress. All right. Okay, so this one we already went over. Okay, so here just a quick clarification about the notation. All right, so about normal stress and shear stress. Okay, so sign convention. Okay, when you have in general, when you talk about one spot, there's stress on it. So if you cut the surface there, right, the normal stress will be positive away from the surface, follow the surface normal direction, and the negative if it's compressive. If it's press on it, it's negative, right? So that's an easy sign convention view, right? Consistent all the time during this class. Okay. Another one is for the shear. Okay, it's a little bit tricky here. So the shear we define if you have a spot, you can cut a cubic out, right? That spot, if you cut a cubic, okay, the shear defined positive if it's on a positive surface and it's follow a positive direction. Okay, that sounds weird. Okay, so let me explain. First, what's a positive surface? The surface normal is along the positive x direction, or the surface normal is follow the positive y direction, or the surface normal follow the positive z direction. That's what we call normal, positive surface. Right? Vice versa. If you have a surface against the x direction, say this in this case here to the left, x to positive direction is to the right. So that's what we call a negative surface. Okay. So if a shear stress on a positive surface is along the positive direction, follow the positive y, and that's a positive stress. Okay. On the other side, on a negative surface, if the shear stress is pointing downward, it's positive. Right. Yeah. So what we show here are all positive. Let me put it this way. Okay. This is a 3D situation. Now, if you look at the picture on the right, that's a 2D. Actually, we're more focused on 2D, right? So make sure you can at least get the 2D part correct, know which direction is positive. Okay, if you look at the picture on the right, so this one here, this is positive stress because it follows the positive direction. So this positive stress follows the away from the surface, right? So that's positive direction. It's tension, basically positive. This one, away from the surface, tension, so it's positive. This stress, away from the surface, so, pulling on the surface, so it's positive. So all this normal stress are positive. Now, this shear stress here, it's on a positive surface and point to the positive y direction. So that's a positive shear stress. This is positive. Okay. This one, same. On a positive surface, follow a positive direction. So that's positive. Right. Now this one, this shear stress here, it's on a negative surface to a negative direction. So negative, negative, so that's positive. All right. So all this components show here, that's the positive one. So anything against it will be the negative, or opposite will be negative. Most of the time, it's actually not a big issue when you try to identify. It's very easy to remember because you can easily remember. Okay, here this one is positive. Can everyone remember this one on positive surface, right? And then that's according to this one, matching this one will be positive. For example, you have this element here. Okay, so this is a normal direction. So you have a normal shear here. Not normal shear. You have a positive shear here, right? With this shear, you must have a shear here as a pair. So this pair is positive. So we talk about deformation, always pair, right? A pair of normal stress, so sigma, sigma. You have to have a pair. So that's all positive. Then this shear, all positive. And then for this one, you must have this one to balance it. Therefore, that's also positive. So they're all positive. That's how you kind of understand it, and the way you can easily remember which way is positive. Right. If you try to remember it one by one individually, that's hard. But you remember as a system, usually this four must be together. If I change the direction of this one, then all other three must change. Otherwise, it won't be in balance. So therefore, all these four are positive. If I go the other way, then all the other four will be negative. That's the easy way to do it. You have a question?
Okay, so I have to be cognizant of three directions. I have to work on my bending, my normal stress, my shear stress, and how they relate to positive or negative sides of that cube.
For the cubic, that's the same. First, this 2D. Everyone follows the 2D. Right now, the same thing. 2D, you just add another surface. That becomes 3D. But the rule is the same. This front here, I think in this picture here, Z is the front, right? Z is pointing this way. So on this front surface, positive Z direction, positive surface. And if you have a shear component, actually they don't show anything there. There's nothing there, because now we talk about 2D. Plane stress. So there's nothing on this Z surface. You see there's no error on that surface.
I'll wait for an example. I'm just wondering how the sides, the direction of the sides will correlate
Okay. I think once the problem comes, the examples come, you'll get a better thing. Here, I'm just trying to throughout this, clarify the definition. Right? Okay. We'll have a lot of time to actually say which one is positive and negative later on as well, with the examples. All right. Okay. Any other questions here? All right. If not, let's move on. Look at the one more thing here. Okay, so that's the sign convention. Okay, another thing we want to cover is, okay, remember we talked about the stress at one point of any structure, right? So if I have this coordinate, okay, I'm standing here, I'm trying to look at what's the stress there. So basically I have an X here and I have a Y in this direction, vertical, right? So now you have the stress component. You have on the left, that's basically all the stress component. Let's say I know this. I can basically measure or I can calculate, right? So I know all the stress component. Now, what if, okay, somehow you're looking at a different direction. You're looking at the X1, Y1 direction. In that direction, what will be the stress? You're going to have a new element, right? If you look at the X1, Y1 direction, you're cutting this square. What will be the stress component? Why would you care? Change from here to here. One reason is when I have a complicated structure, right? Sometimes I cannot use just one coordinate system. You know, the structure is curved. So therefore, here I have this XY. Here I may have a different XY. So I may need this different XY. So you need to know the relation how the stress will change when you change the XY system. That's one reason. Second, we need to find out whatever the stress in any direction, so we can figure out in which direction the stress will be maximum. Then the material may fail in that direction. So we can predict, oh, the crack is going to generate along this direction. And actually, we already know in chapter 2, we know, oh, 45 degrees, that's the maximum stress. It's going to crack along that line. Chapter 3, similarly, right? If it's fail by normal stress, then you're going to fail along 45 degrees. So now it's more general, more systematically. We say, okay, in any direction, what will be the stress? So we need to know that information. So therefore, our task here is find out, if I know the stress in this current XY coordinate system, what will be the stress component in this X1, Y1 direction? All right. It's similar like in chapter 2, 3, we say, oh, I know the cross-section. On the cross-section, what's the stress? Then what would be the stress on inclined surface? It's a similar question. Okay, so here is just more general. You have all the component, sigma x, sigma y, tau xy, and rotation angle in any direction. Now, how can we find this new component on this new surface? How did we find it back then in chapter 2, chapter 3? What's the approach? Yeah, we have an equation there, right? Like, remember, sigma equals to sine, cosine, all this relation, right? Okay, so how did we get that? What's the approach we used back then? Free body diagram. You make a cut, right? So if I want to know, okay, what's the stress on, let's say, in this direction? This is the x1 direction. I want to figure out what's here. So basically, I can make a cut here. I cut this direction. So this direction, right? So say I cut this element. So I can look at this element. What will be the stress? And that's what we do here. So you cut this element, that's a triangle. And that direction, this direction is actually where you are care. You want to figure out the theta direction. So we can cut this way. Once you cut it, this is a free body. Then you can basically write the equation of equilibrium. So sigma fx is supposed to be 0, sigma fy is supposed to be 0. So remember, right now you label all this just stress. But stress, you can times the area, you get the force. So it's a force equilibrium. So you must use sigma fx equals 0, sigma fy equals 0. Or you can use sigma f theta equals 0. And then sigma f theta plus 90 also be 0. So you can use both two sides of the equation. You can use either one. They all should be true, right? Because the equilibrium, any direction, suppose the force add together be 0. So you can use either the top two or the bottom two, whichever you feel more comfortable, or quickly give you answer, easy to give you answer. Yes.
In the diagram for the forces, why is our normal stress parallel to the surface that is normal?
You talk about which surface?
The right picture?
The right side?
The inclined surface.
Yeah, on the inclined surface?
Yes, on the right picture, it says that the normal stress is parallel to that inclined surface instead of perpendicular.
Oh, that's just calculation. What's the amount? They just say, this is shear. Definitely, that's shear stress. But what's the amount of this shear stress? Equal to something like that. So ignore that one on the right. Just look at the left one. Okay. So basically, that's all the stress components. So on this surface, you're going to have a tau, you're going to have a sigma, right? And that's we don't know. That's the one we want to find out. So how can we find it out? I can write one equation in this direction, all the force equals 0. And then I can write another equation in this direction, all the force equals 0. So I think I have the equations here. So in the x1 direction and the y1 direction, all the forces must be 0. Right? So based on that, I can just get everything together. That's what we did actually in chapter 2, chapter 3. It's the same idea. Okay. So that's just mathematical derivation. And you can check the textbook, read the detail there. All right. And here's just the result. I think we'll care more about the result, how to do it, know how to do it instead, not the mathematical detail there. I want to save a few minutes so we can go to look at the exam too. All right. Okay, so this is the result. Now, I just want to comment on this result. Now you see here, what's different from chapter 2 and chapter 3? What's different now, this result? Now I have 3 equations. Before we just have 2. What's the sigma theta? What's the tau theta? We only have 2. Now you have 3. Right? Because you rotate that element, so you have this x direction and y direction. Okay. Fundamentally, there's still 2. Because sigma x1, sigma y1, I'll say there's the same equation. Or I'll say similar equation. Why? Because x1, let's say it's this direction, in the theta direction. What if you change it, turn more, make theta plus 90? That's y1. So therefore, if you change the theta in the first equation, add 90 degree, you'll get the second. So they're actually related. The reason you want to write this 2, because we're talking about now you have a square element. Initially flat, you rotate it, and you have x1, y1. So that will give you 2 there. That's the reason you have 2 there. Okay. Fundamentally, there's the same thing. You just rotate 90 degree more. That's it. Okay. Now, secondly, now each equation, you have more terms. Right? The reason is now we don't just have a sigma x. Right? You have a sigma x. You also have sigma y, and you have a tau xy. That's why each equation now you see more terms there. Right? You see here 2 parts add together. In this one, 3 parts add together. There's 3 parts there. So you have both sigma x, sigma y, and tau xy. So therefore, this equation now is a little bit longer. All right. Okay, so with this equation, if I give you any direction, I say, okay, what about 25 degree? You plug in 25 degree there, you'll get the stress component in that new direction. Right? I give you what angle, you can put 45, you can give 29, 36, whatever degree you put there, you get the stress in that direction. Right? So now we're done. We can find out stress in any direction, business direction. So what we want to learn next is, based on this equation, what's the relation? You know, when you turn different degrees, is there any rule that kind of make it special, that something control it? And that rule is actually, okay, it's your homework. Look at this one. Check out the equation. Okay, so I can change the equation, the first equation, into this way. Sigma x, right? I can move this term to this side. I mean, right? You can just move around, play with it. Okay, the second equation is here. Now, what if you square this one? So you square here, and then you square here. You square here, and then add them together. What do you get? That will be this equation. Okay, it's up to you. After the class, you can prove it. I'm getting the correct. Okay, now if you look at this bottom equation, what kind of equation is this one? When you change the theta, right? When you change theta, the sigma x1 going to change. How x1, y1 going to change? But they follow this relation. What kind of relation is this? It's a circle. Does this look like x minus a plus y square equal to r squared? Is this the same? Is this the same? These two equations the same? See here, this sigma x1, that's the x. Tau x1, that's the y. So basically x squared plus y squared equals a squared. That's a circle. So we get the conclusion, okay, when you rotate your coordinate, okay, the stress is going to change, but they follow a circle, right? So we can actually use this relation to find out stress in any direction. And that's what we call Moore circle. And we're going to talk about Moore circle in the next couple of lectures. So want everyone be able to draw a circle. Well, we can all do it, right? But draw a Moore circle. That's the first part. Second, use the circle to find the stress in any direction. Okay. So we're going to do that next time. All right. Any questions here? Very good.